What if I told you the universe has a hidden rule book, and every page says the same thing? You can get close, but you cannot cross this line. You cannot go faster than 299,792,458 meters per second. You cannot cool anything below -273.15 degrees Celsius. You cannot cram more than 2 electrons into the same quantum state, and you cannot pack a dying star heavier than 1.44 times our Sun into a white dwarf without it detonating. These are not suggestions. They are walls built into the architecture of reality. For centuries, physicists assumed the universe was smooth, continuous, and infinitely divisible. They were wrong. Nature runs on steps, not slopes. And the moment we figured that out, it changed everything. Let's start with the crisis that blew the doors off classical physics. It is the year 1900. Physicists are studying something called a blackbody, an idealized object that absorbs all radiation hitting it and then re-emits energy based purely on its temperature. Think of a piece of iron heating up. It starts glowing red, then orange, then white. Classical physics had an equation for this, the Rayleigh-Jeans law, and at long wavelengths it matched experiments beautifully. But as you crank the math toward shorter wavelengths, toward ultraviolet light, the formula predicted that the blackbody should blast out infinite energy. Not a lot, infinite. Physicists called this the ultraviolet catastrophe, and it was classical physics predicting that the universe should have destroyed itself in a blaze of limitless radiation. Obviously, that had not happened. Something fundamental was broken. Enter Max Planck, a 42-year-old professor at the University of Berlin. Planck was a conservative thinker, deeply committed to classical physics. But he was honest with the data, and the data was screaming that energy could not be continuous. In what he later described as an act of desperation, he proposed something radical. Energy is not emitted in a smooth, unbroken stream. It comes in tiny, indivisible packets he called quanta. The energy of each packet was tied to its frequency by a new constant, now called Planck's constant. A number so small it is 6.626 times 10 to the negative 34 joule-seconds. At everyday scales, energy still looked perfectly continuous, like how a staircase with trillions of microscopic steps would look like a ramp. But at the atomic scale, those steps mattered enormously. Planck's formula perfectly matched the blackbody experiments. The ultraviolet catastrophe vanished. But Planck himself spent years trying to force his quantum idea back into the classical framework. He could not. The universe really does deliver energy in discrete chunks. Now, this idea of discreteness goes far deeper than just light. Think about atoms. In the early 1900s, the best model for an atom looked like a tiny solar system, electrons whipping around a nucleus in neat orbits. The problem: according to classical electromagnetism, a charged particle accelerating in a circle should constantly radiate energy. An orbiting electron should lose energy and spiral into the nucleus in less than a trillionth of a second. Every atom in the universe should have collapsed almost instantly. That obviously did not happen. So again, something was fundamentally wrong. The solution came from treating electrons not as tiny planets, but as standing waves wrapped around the nucleus, like the vibrations on a guitar string. When you pin down both ends of a string, only certain wavelengths fit. You get the fundamental frequency, the first harmonic, the second, and so on, but nothing in between. Similarly, only certain electron wavelengths fit around the nucleus, and each allowed wavelength corresponds to a specific energy level. An electron in one of those states cannot smoothly spiral inward. It would have to jump to a lower energy level by emitting a photon of exactly the right energy. And there is a lowest rung on this ladder, a ground state, below which the electron simply cannot go. Discreteness does not just describe atoms. It saves them from annihilation. And this principle does not stop at the subatomic. The speed of light is arguably the most famous limit in all of physics, sitting at roughly 300,000 kilometers per second. Nothing with mass can ever reach it. This is not a technology problem. It is geometry. Einstein showed that space and time are woven into a four-dimensional fabric, and the speed of light is baked into that structure. As any object accelerates toward light speed, time slows down, its length contracts, and its effective mass climbs toward infinity. You would need infinite energy to push even a single grain of sand to the speed of light. The universe makes it mathematically impossible. Then there is the temperature floor. Absolute zero sits at 0 Kelvin, negative 273.15 Celsius. The third law of thermodynamics says you can never actually reach it through any finite number of steps. Each step of cooling gets you closer, but the effort required grows without bound. Scientists have gotten impressively close. In 2021, researchers achieved 38 trillionths of a degree above absolute zero using ultra-cold rubidium atoms. But a true zero? The laws of physics forbid it. For the same structural reason the speed of light is unreachable. Nature draws a line and says, "This far, no further." These limits even dictate how stars die. When a star like our sun exhausts its nuclear fuel, its core collapses into a white dwarf, held up by electron degeneracy pressure. This pressure comes from the Pauli exclusion principle, a quantum rule proposed by Wolfgang Pauli in 1925, stating that no two electrons can occupy the same quantum state simultaneously. This forces electrons into higher and higher energy levels, creating outward pressure that resists gravity. Without the Pauli exclusion principle, all matter would collapse. Your body, this planet, every solid object would implode. But even this quantum pressure has a ceiling. In 1930, a young physicist named Subrahmanyan Chandrasekhar calculated that if a white dwarf exceeds 1.44 solar masses, electron degeneracy pressure loses the fight against gravity. The star cannot hold itself up. It either collapses into a neutron star, detonates as a Type 1a supernova, or, if massive enough, becomes a black hole. This threshold, the Chandrasekhar limit, is another discrete boundary that nature enforces without exception. So here is the deep puzzle. General relativity describes space and time as perfectly smooth, a continuous fabric divisible without limit. Quantum mechanics says the opposite. Energy, angular momentum, and particle properties come in discrete packets. These two theories are the most successful in all of physics, yet they fundamentally disagree about whether reality is smooth or granular. Unifying them is one of the biggest open problems in science. Some approaches, like loop quantum gravity, suggest that even space itself may be quantized at the Planck scale, roughly 1.6 times 10 to the negative 35 meters, a distance so small that a proton is a trillion times larger. What we know for certain is this: every time physicists assumed the universe was smooth and continuous, nature corrected them. Energy is quantized. Electron orbits are quantized. Speed has a ceiling. Temperature has a floor. Stellar masses have breaking points. The universe is not a slide. It is a staircase, and every step is load-bearing. If this made you rethink how the universe operates, drop a like and subscribe so you do not miss what we unpack next. And tell me in the comments, do you think space itself is made of tiny discrete units, or is continuity hiding something deeper?